So in this way, we have proved that this family is a partition of set X. Hence, you can write, hence phi rho is this of subsets of X is a partition for X. All of you can by write yourself. This family of subsets of X is a partition of X. We have proved. Now, next part is that conversely, if pi is equal to ai, I belongs to I, is a partition of X. Then the relation psi pi x comma y belongs to X process such that there exists I belongs to I xy belongs to I is an equivalence on X, is an equivalence on X. So let rho be equivalence on set X, then the family phi rho. If pi is ai is a partition of X, this set is a partition of X, then what we have to prove? First we have proved that this is an equivalence relation on X, then this family is partition of X. Now conversely, what we have to prove? That if this is partition of X, then this relation is what? Equivalence on X. So we have to prove that this relation is equivalence on X. We have to prove some more thing, but first I will prove this, then I will write later. So see the proof of it. See, you have to prove that psi pi is what? Reflexive, symmetric, as well as transitive. So as we know that since pi is partition of X, therefore ai is non-empty for every I belongs to I, correct? So of course there must X belongs to ai. There must exist some where X belongs to where? X. There must exist at least one element in ai. X belongs to ai. So now if you say if X belongs to ai, it implies what? It implies what? If X comma X belongs to ai, it implies that X comma X belongs to psi pi, because you see X comma Y belongs to psi pi such that there exists some I belonging to I. X comma Y goes in ai. So if X comma Y goes in ai, then that XY goes in psi pi, correct? So here what happened, every ai must contain some element. X goes in ai, so X comma X will go, and different X goes in different aj, for example, then again that x comma x, yeah, you can say y comma y goes in psi pi. So in this way x comma x belongs to psi pi for every x belongs to x. Correct? Because you see ai is non-empty for every I, and x belongs, this is all arbitrary. So arbitrary, so x belongs to ai, x belongs to x, so x comma x belongs to psi pi. It implies that psi pi is what? Reflexive. Now you have to prove that psi pi is symmetric. So let x comma y belongs to psi pi. It implies that there exists I belongs to I such that x comma y belongs to ai, x comma y belongs to ai, or you write y comma x belongs to ai, both are same. It means that y comma x belongs to psi pi. So it implies that psi pi is what? Symmetric. So in this way psi pi is symmetric. One thing I like to clear here, see, to prove psi pi is reflexive, x comma x belongs to psi pi for every x belongs, we have to ensure that all x are covering here. So well, we know two things here, that the ai is non-empty, and you know that x is equal to union of ai, I belongs to I. So if you talk about any x belonging to x, x will go into some ai, isn't it? If you talk about that is x belonging to x, that is the union of ai, it implies that x belongs to ai for some I. So when x belonging to x and x is written as union of ai, so every x in x goes in some ai, you can say, and when it goes in ai, well, we know that x comma x, of course it will go in psi pi. So in this way all x are covered. So x comma x belongs to psi pi for every x belongs to x. So psi pi is what? Reflexive, and that was symmetric. Now what we have to prove? We have to prove that it is transitive also. Let's see how we prove transitive. We have to prove psi is transitive. So see, what we do, take any x comma y and y comma z belonging to psi pi, then there exists I comma j belonging to I such that, you see, xy goes in ai and y and z goes in aj. Now look one thing, that xy goes in I and yz z goes in aj. So one element is common between these two, and as ai, family ai forms a partition of the set x, and so either ai or aj are disjoint, and if they are not disjoint, if they have some element common, if there are two cases, either they are disjoint or they are equal to each other. So here you see that one element is common, so it means that they are not disjoint. So if they are not disjoint, being a partition, they will be equal to each other. So since y belonging to ai intersection aj, therefore ai is equal to aj as pi is partition of x. So therefore you x comma z both belongs to ai is equal to aj. So it implies that x comma z belongs to psi pi. So it means that psi pi is what? Transitive also. So psi pi is reflexive, symmetric as well as transitive. So we can say that hence psi pi is equivalence relation on, of course, x. So in this way this part is also proved. Now the last parts, what we have to do, you see, we have to prove that for every relation rho on x, psi phi rho is equal to rho, and for every partition pi of x, phi psi pi is equal to pi. So we have to prove that for every relation rho on x, psi of phi rho is equal to rho, and for every partition pi of x, we have to prove that phi of psi pi is equal to pi. So try to understand one thing, that this on the left hand side is what? It is again a relation, and here on the left hand side it is again a partition. See, when rho is equivalence relation, we have to prove that this is equal to this relation. And when pi is a partition, we have to prove that pi is equal to this partition. Correct? So now let's start. Proof. So you start from here that x comma y belonging to psi phi rho. It implies what? When x comma y belonging to psi of phi rho. Psi rho is what? Partition. Here pi is partition. So of course x comma y when belongs to psi of phi rho, it means what? It means that see, when x comma y belongs to psi pi, it means there exists some I belongs to I such that these xy goes in ai. So here what happens? Here it implies that when x comma y belongs to psi phi rho, it implies that x comma y belongs to x rho by definition. So it implies that y belongs to x rho. So it implies that x comma y belonging to rho. So in this way, this is the subset of, we have taken a limit here and we have shown the here. Why? See, when x comma y belonging to psi of phi rho, correct? It means that these x comma y belonging to any you see that it belongs to in any of the subsets of this. that is x comma y. Of course, we know well that y and x will go in ai, correct? You see, when x comma y belonging to psi pi, then x comma y belonging to ai. Of course, well, we know that y and x goes in same set, correct? ai, and we know that x goes in x row. X goes in x row, so y also have to go in x row, correct? So in this way, y belonging to x row and x comma y belonging to row. So in this way, it is. Now, if you go reverse, then what will happen? If you go reverse, then what will happen? See that if you go, that is, if you take x comma y belonging to row, then y belongs, of course, to x row. Then you see y is going in x row and x is going in x row. So of course, this x comma y belonging to psi of y row. So in this way, this reverse part is also proved. This is proved. Now we come to this one. This one. Now you see that phi of psi pi. This is what you see. What is phi of rho? Phi rho is what? X row such that x belongs to x. So here same, you write x psi pi such that x belongs to x. Same situation here. So x psi pi, and what x psi pi? You know that psi pi is what? Psi pi is what? Equivalence relation. So x. So what is the value of x psi pi? Psi pi is what? Equivalence relation. So x psi pi contains what type of elements? It contains those elements of x such that is y belonging to x such that x comma y. You write just like this. Like this, x comma y belonging to psi pi. X psi pi contains those elements of x such that when x and y are related to each other, psi pi related, x comma y belong to psi pi, correct? So now try to understand what it is. When x, y are going in psi pi, when x, y are going in psi pi, isn't it? Then y is going in ai. Y is going in ai. So in this way you see that it will cover like this. For example, ai and ai belongs to pi, and this is what? Whole pi. Y belonging to x such that xy belonging to psi pi. So y belonging to x, xy, whenever x comma y goes in psi pi, it means what? It means what? It means that that xy are the member of ai, correct? Y is the member of ai, so it covers all ais, It covers all ais. So in this way, ai such that ai belonging to pi, so it will be equal to what? Pi. So in this way, pi is equal to phi psi pi. So both becomes equal to each other. Now we do some examples and one fact also that fact is that intersection of equivalences on a set X equivalences on a set X is again an equivalence. And this I left for all of you as an exercise, very easy. You consider a family like this, rho I. Rho I is what? In equivalence. So if each rho I is equivalence, you have to prove the intersection rho I is also equivalence. That is, intersection of rho I is also reflexive as well as symmetric as well as transitive. Very easy. It's trivial. So this is the first fact. Second fact is that union of two equivalences need not be an equivalence in general. Union of two equivalences on a set X need not be an equivalence in general. But we have to support this by an example. So let's see example. What you consider a set X, A, B, C, D. Now made partitions, pi 1, pi 2 is partitions, that is A, B and C, D and A, C and B, D. Try to visualize that pi 1 as well as pi 2 forms partition of set X or not, correct? So pi 1 and pi 2 forms partition of set X. Partitions of set X. Both are partition. Means this is A1, you say this is A2, this is, you say B1, this is B2. Now all of you can see that A1 union A2 is what? X. A1 union A2 is what? X. Here B1 union B2 is what? X. And if you take the intersection is what? Empty. And also A1 and A2 are what? Non-empty. So they follow all the things which is required to make a partition of the set X. So pi 1 also forms a partition on set X and pi 2 also forms a partition on set X. Now you see, now I am just writing the relation, equivalence relation. Rho pi 1 is what? A, B, B, C, C, D, D, A, B,